Hello, in this tutorial I'll be taking you through scheduling. In the book they're calling it CPU scheduling. This is from Silvershot's 9th edition, chapter 6. And I will try and pick from other textbooks as well, so there will be some things I'll cover in some detail that are not discussed in the textbook. CPU scheduling doesn't have to just do with computing. It can be applied to many other areas in real life. It could be banking, it could be inventory management. There are many applications. I'm hoping that you take away at least a lot from this specific topic. You don't have to know anything about programming per se to understand or appreciate scheduling. And remember, the mindset is you should listen. I encourage you to read the textbooks. There are many other tutorials online. I encourage you to explore. There are a lot of examples throughout this exercise. You can pause it and see if you can get the same answers I get. Make sure you're following along, and make sure you think about what you hear, what you see, and what you try. Right. So we want to make sure that we understand how schedules are used. We will be looking at different ways for evaluating schedules, because for many things in daily life, whether you're buying a computer, memory, car, plane, motorbike, book, there has to be some criteria. So we'll discuss what are these criteria when discussing schedules. We'll look at a few of the algorithms that exist for computer scheduling or any other type of scheduling. And we'll look at the criteria specifically for evaluating and looking at the specific schedules. And then I'll discuss some issues such as going from single core, multiple core. I should have said multiple core, because most books tend to think about single core scheduling, but in this I'll try to do multiple core scheduling as well. And finally, I'll look at some real-time algorithms. I'll not go too much in depth because I'm sure the examples you have seen will help you construct your own charts. Right. Now, this is the state diagram for processes. Now, when processes are created, they get admitted into the ready queue, and then when they are ready, of course they are ready. If there's nobody running, they get to run. An interrupt, maybe an IO event, something could happen from outside of the process, that's this interrupt. And if the process asks or requests for some sort of IO, it'll go into the waiting queue or waiting state. And when the item it's requesting becomes available, moves to the ready. Now, if you look at this diagram, it means that as far as the resources that a process uses, and you'd see these terms in the text or any other discussion, there will be CPU bound processes and IO bound. CPU bound meaning it's spending time on the CPU. IO bound meaning it's asking for some sort of IO, could be disk, could be memory, could be some device it wants to use. So when we are discussing processes, most processes move between CPU and IO. Right? So maybe it does some calculation, maybe reads a file, does some calculation, prints to screen. So there's this interleaving between CPU and IO. Usually when someone says, oh, this process is CPU bound, it means often that it's going to spend a lot of time on the CPU. And when people say, oh, this process is IO bound, it means it's going to spend a lot of time on the IO. The reason why we would like to be able to schedule is most of the time it will happen that some processes may actually do some IO that's requesting for devices, and they'll be moved from running to waiting. And that would mean that the CPU is being wasted. In that case, there has to be a scheduler who will move people into running to make sure that the CPU isn't wasted. There are also other cases when we don't want just to get, let's say, a specific process running all the time. So in computing, there's this preemptive and non-preemptive. Preemptive meaning we can stop processes and do other things. Non-preemptive meaning once processes start to run, they run forever until they yield the CPU. Right. So if we look at the core part of the scheduling, now remember that there were other types of schedules. You can see there's a long-term, medium-term, short-term. We are dealing with the short-term scheduler, the CPU scheduler, who's actually dealing with moving people in. Now what I've done is to list out the different transitions that occur for processes. And I want you to pay attention to the ones where sort of it yields. So if a process is running and it decides to exit, that means it is yielding or it's being cooperative. And I think the word I'm using is non-preemptive. So it sometimes when a process is doing something, it just voluntarily gives up the CPU. So if it exits, it's giving it up voluntarily, and if of course it asks for IO and the IO is not ready, it's more or less agreeing to give it up, right? But there are other times when it doesn't have any say in what's happening, and that is when an interrupt occurs. So when an interrupt occurs, the process has no control to know, oh, an interrupt occurred. No, it's the system as a whole, the kernel saying maybe, hey, or the hardware say an interrupt occurred. So that's outside of the control of the process. And of course, once you are waiting and an IO has completed, you don't have control of that. So there are some cases where there is some sort of cooperative idea of scheduling. So if you yield the CPU, the scheduler can then say, oh, you are cooperative, let me go and pick somebody to come. Or if you did an IO event, let me go and pick somebody. But anytime, for example, if a device becomes available, the scheduler will check and see, should I go and deal with moving people from the ready queue to the running queue? And anytime an interrupt occurs, again, the scheduler would have to go through and say, should I schedule people on, make them running? Right? So I've highlighted just a few. Right? Now, if you look at the criteria, so when we are trying to discuss is a scheduler or scheduling good, we try and discuss some criteria. Just as if you are buying a book, you'd say, is the book hardcover or softcover? Is the book maybe printed colored or black and white? Is the book maybe having a certain number of pages? Is the book maybe a first, second, or third edition? So anytime you are using something, you try to rate it in a way, and that's what we try and do with schedules. So when we have a schedule, we discuss a few things. So, and these are all important. For example, we ask, are we utilizing the CPU? So I should have said CPU utilization or CPU scheduling. So we'd say maybe it's 80% utilized or 100% utilized. If you have any type of task manager, so this is a task manager by sysinternals, and you can see, for example, that it's saying how much it's using of the CPU. It's saying 20% or so on. It even has a graph showing you how much of the CPU it's using. And in this case, I think I have, let's see, probably 2 CPUs, 2 cores, right? There's also IO. So it's also giving an indication of how much IO or input output is going on. And in my case, there's even a specific graph for specific chart showing graphics. So whatever type of scheduler that you have, it needs to keep a lot of statistics. So that you can, as maybe an engineer, systems administrator, architect, know what's going on. So CPU utilization is the first one. Throughput is the number of processes completed per second. Let's say if you have a web server and people are visiting pages, you could say, oh, how many pages can I serve to my users? Someone can say, oh, I can give 1,000 pages per second or 2,000 pages a second. Or maybe you are printing to screen and someone says, oh, I can print the output from 60 things per second. So there's this idea that you can get a certain number of items per second. Another common, I think, it's not in CPU scheduling, but it's something you may have heard of, is maybe frames per second, especially when you're doing audio, video processing, or maybe 3D processing in games, or some sort of reporting or animation. There's this idea that you get to complete a number of things per second. So that is throughput, the number of processes per second. There's also the turnaround time. That is, when someone or a process asks to do something, how much time does it take between when it asks that the submission until when it finishes? There's also the waiting time. That's how much time is it waiting in a queue. So let's say if you enter the banking hall and you join the queue, and from the time when you're standing in the queue, maybe you get to the teller and the teller says, oh, please wait stand aside and let me serve a few more customers while your request is being handled by someone else. All that time you spend, and usually in the CPU, it's the time you spend in the ready queue, we call that the waiting time. From the textbook definition, they are not actually adding the time you are in I/O. Right? There's also response time. For any program, for example, when you start a program, you will see, so for example, if I click Task Manager, there it appears. So the time between when I clicked it, asked for it, and when I first saw something, usually is the response time. So for interactive processes, maybe when you click, you see something, you click. So that sort of, when something is starting up, how long between when you made the request and when you see something, that is the response time. It doesn't mean when the thing actually finishes running. It's when you first get some output from your process. Right. So now we've seen these, let's move into some specific types of schedules. Now I'm sure you've seen all of these before in some form. First come, first served is very common. In banks, at the canteens, maybe in traffic, whoever gets there first gets to move, right, or gets to access the resource. So if you go and buy something from a shop, we'll assume that if you get to the cashier first, then you get to pay first, and anyone who comes after you follows. Right? Shortest job first. This is something that you should have or probably have seen in some queues as well, where if someone wants to just use, I think those of you who come to my office hours, sometimes I ask people, is your question very long? Especially when someone is seated. I'm talking to someone and you ask a question. I'll ask you, is it going to take a long time for me to answer your question? If it will take me a short time, maybe 3 seconds or 5 seconds, I would usually let you jump the queue, meaning that I am actually practicing shortest job first, meaning the person who has the shortest job gets to ask me or gets to utilize the CPU first. That's, okay, in this case, I'll be the CPU. There's also priority scheduling. Priority scheduling means that every process would have a priority. So, for example, if you come to office hours, usually those people that I advise or supervise have higher priority. If you've booked or made an appointment, you have very high priority. If you just walked in, you will have a low priority. So there's this idea that we can schedule processes the same way. For computers, keep in mind that, for example, if you have a task manager, right, so there will be many things running in the task manager. And what you'd see, for example, is there are, at least Windows does this currently, there are these things called the applications, and Windows also has, this is the background processes. Right. And if you pick the process and you went to properties, usually every process, let me see if it can resource values, disk memory. Okay, so this one doesn't give as much. Let's see. Okay, so it has the name, what's running, the memory. Okay, so at the very least, even though there are many processes running, I am sure, so if you look at these, you can see the usernames, that some of them belong to someone called the network, some of them belong to myself, and some of them belong to the system. So one way, for example, is the computer could decide that depending on who is running it, the username of the person, you'd be maybe a high priority process. So priority runs also in computers. Right. Let me also show you something interesting that you can do with the Process Explorer from sysinternals. So this is the Process Explorer from sysinternals, free to download. And one of the things I find interesting about this is you can actually set the priority of processes. Let's move it this way so you can see what the option provides. So it says real time, high, above, and so on. So right now it says normal. In background, that means low priority. So an idle is even, well, less. But it says when it's in background, it actually has I/O, low I/O and memory priority as well. So it seems that for how the CPU deals with things, it keeps track of who has priority and so on. Right. So processes do have priority. Now, round robin actually means that you are allowing everybody who is available to have a chance, not to run all the time. Now, if you look at, I'm going to sort this by CPU. I'm just going to, okay, so you can see that the list here keeps changing. So if you look at the list, maybe someone comes up a bit, someone drops down a bit, and so on. So it sort of keeps changing. So it means that the CPU is not allowing just one person to run all the time. What it's actually doing is it lets someone run for a bit, and then, like, you can see Process Explorer moves up and moves down, moves up. So it means that it's actually moving around and giving everybody a chance to run, or at least as many people a chance to run as possible. Now, there's also this idea of multi-level scheduling. Now, the idea of multi-level scheduling would mean that, and I'm going to use the task manager from Windows. So, for example, you can see that it has grouped the processes into apps, that's the things that are running, I'm interacting with, background, maybe some services, and Windows processes. It means that as far as Windows is concerned, there are actually 3 groups of programs. Some of them are called Windows processes, so I'm talking now about multi-level scheduling. I also have another group that's called background. Let me see if I can, I think I've gone all the way to, these are apps, okay, background. So it means that since I have 3 or 4 groups, and depending on the CPU and also the type of kernel operating system that you have, the operating system could be keeping track of 3 or 4 different types of schedules for different groups of software. And this is called multi-level scheduling. Right? So it means you don't always have to always be first come, first served. It could decide, oh, the apps are going first come, first served, the system processes are going priority scheduling, and maybe the background processes are going round robin. So the multi-level scheduling idea means that we can combine many of them and have multiple queues and do different types of scheduling depending on the category of the process. Right? So we've been reading a lot. Let's move into some examples. Now, the first one I would like to point out is anytime you have a schedule, you have some sort of ready queue. So there's some queue, there can be one or more. Remember that if you're doing multi-level scheduling, that means you could have several queues. But if you're doing a simple one, maybe there's just one queue. And what we usually do is we would move or select a process from the ready queue and send it to the CPU running. Sometimes you can have 2 or more processes running at the same time. Right? So I would point out that if you're doing multi-core processing, that means that I can have 2 or 3 or 4, maybe 8 running at the same time. This type of scheduling is similar to what is done for threads. Right. Now, when it comes to first come, first served, usually means whoever gets there first. If there's nobody running, you go straight to running. Right. Now, as more people come in, they will have to queue up. So as people show up, they have to join the queue, and then that means that when a process is done from the running, it would allow someone from the queue to now start running. Right? So that's first come, first serve. So whoever comes first gets to run first. Now, I should point out that I am describing non-preemptive schedules. So remember I said there's preemptive and non-preemptive. Preemptive meaning I could interrupt you and run you. In this case, I'm just saying when you run to the end. Right? So you also have priority queues. Priority queues are a lot like first come, first serve, or even shortest job first. I put the two together because I see both shortest job and priority scheduling as a type of scheduling where you set a priority. The priority can be based on maybe some value. Maybe you can say, oh, all processes by clients has a priority of 5. All processes of anonymous users has a priority of 1. All processes of logged in users, so that's like a website, has a priority of 20. And you also have to be consistent as to how you assign or rank your priority. Sometimes they'll say the higher the number, the higher the priority, or the lower the number, the lower the priority. So when you are unsure, simply check. Just I would say ask if you don't know the system very well. So for example, I am going to pick one of these processes over here, priority, and it means that in this case Windows, the higher the priority, like 24, that means it's very high, the higher the number for the priority, the higher it's assigned, and the lower, like 4, that means the least, right? So always make sure you check. If you're in an exam scenario you don't know, just check. Though I don't think it's something very complex. So if it is a shortest job first scenario, that means whoever comes in gets to run. But for the priority, we could just say it's like a set of items and you pick one of them to run. So that is the whole idea with this priority for shortest job. Shortest job first just means that the priority is given to the job that has the shortest time. Right. Round robin is like, I always said, it's like a game where everybody takes turns. Right. So once people are in the ready queue, or whoever is in the ready queue would say, okay, you can go and run, and you run for a bit. You don't run until you finish. We give you a fixed amount of time. You can say maybe you get 2 milliseconds or 2 cycles. You get a certain amount of units. Usually the book sometimes calls them quantum or quanta. After you use it up, if you have not finished, you go back to the ready queue and someone else gets the turn. And if that person also runs a bit, that old person also goes back to the ready queue, someone else gets a turn, and back to the ready queue, so everybody takes a turn. So that is more or less how round robin works. Right. Now I'm going to be, I think this is an incomplete slide. Right, so for a schedule I'm going to do some examples. So this is my first example where I have a schedule. If you are unsure, so in this case I just mean time to arrive, the priority, and the time required. The book would sometimes say CPU best, meaning how much time it spends on the CPU. So this could be seconds, it could be cycles. I'm just saying there's some amount of units. Some people go crazy. They want to know, is it hours, is it minutes? Just assume that it's seconds. For a lot of the examples in the text, they may not say seconds, so you can just assume it's a number of cycles. And remember, a processor uses a clock, so it runs in a certain number of cycles. So or some units. So in this case I'm saying let's compute. So this is where you get to see examples: turnaround time, response time, waiting time, and we're going to do it for first come first serve, round robin, shortest job, and also a priority. I'll also show you how to do the graphs, and then we'll do some computations, that is average, minimum, maximum for each of the, for example, turnaround time, response, waiting time. This is something that you need to do. For a lot of my exams and tests, there could be one of these for some other schedule. Right. So first come first served. So what you see is process 0 arrived at 0, next one came at 1, at 2, at 3, and 4, and so on. What I usually do is I draw a grid, or you can call it a Gantt chart if you want. This was generated by a program, and it just puts in n means it's new, it's not started to, it's not yet, it's like null, it's not yet available. But so for example, this process is available at time 0, and so he gets to use P0 gets to run. And remember, it needs, so it says time required is 3, it means it's going to get 3 slots. Meanwhile, P1 came at 1 and P2 came at 2, but they don't get to run because P0 is already running. And I said it's first come first served, non-preemptive. I repeat, non-preemptive. So non-preemptive means you can't stop somebody from running, right? So first come first served, non-preemptive. So whoever came first, P0 came first, gets to run. And then when P0 finishes, we ask, of the 2 people who are now available at the time when this person finishes, which of them has or came first? And this one is actually P1, so that means P1 now gets to run. And when P1 finishes, by the time it's finished, note that there are now 3 processes, 1, 2, 3, that have arrived whilst P1 was running. And that means that when P1 finishes, I have 3 choices, either P2, P3, or P4. But because we are picking the first come first served, it means P2 gets to run, and then P3 gets to run, and P4 gets to run. Now, when we talk about response time, that means the first time we get some input, or some response, and we can usually assume that's the first time you got onto the CPU, you got to give us some information. So P0 was in at 0, so we know that there was no delay. The moment you came, you got to run, so that means response time was 0. P1 had to wait for, it came in at 0, sorry, I came in at 1 but got to run at 3, it means it had to wait for 2 cycles, and that's why waiting time is 2, 3. So I color coded them. You can just double check. Now the response time in this case is, sorry, so the waiting time, remember, was how much time is spent in the ready queue. So all this time they were all ready, so we count that. And response time in this case is the same as, that's for first come first serve, not for all schedules. So you have to ask yourself, for example, P1, this is its response time, the first time it showed up, from the time when it wanted to run till when it showed up. And then we also ask waiting time. How long have you been in the ready queue? It's been in for 2. So that's how we do it. Turnaround time is the time when you first showed up till when you ended. So even though P1 showed up at 1, it ended up here. So that means it spent 4 cycles. That means it spent 2 units waiting and 2 seconds that it needed it got to finish. So you have all these statistics available, and these are the computations you can check. So turnaround time, 3 plus 4 plus 3 plus 4 plus 7 plus 9 plus 9 divided by, then that's the average. Min, you can do the max, and so you can see that at least this is how you do it for first come first served. This is shortest job first. This is very interesting. I'm using the same schedule, but this time, by the time P0 finishes, P1 has been waiting, P2 has been waiting, and the question is, between the two of them, when P0 finished, P1 and P2, who has the shortest job? In this case, it is P1, so P1 then runs. When P1 has finished, there are now 3 people who are waiting, but if you look at it, actually P2 has the longest, P3 second longest, but P4 has the shortest. So if you're doing shortest job first, it means that when P1 finishes, the next person to go is P4, and when P4 finishes, the next person to go is actually P3, and meaning that even though P2 came before everyone else, because of shortest job first, the order changes, right? And one of the things I would, so if you just look at the response time. Response time for this one is 2.6, waiting time is 2.6. This is with shortest job first. Let's go back to the first, and you'd see that for first come first served, the response time tends to be longer, so in this case 3.8, than when we are doing shortest job first. And this idea makes sense, because if you consider let's say 2 people, right? One person wants to use the CPU for 1 hour, the other person wants to use the CPU for just 1 minute. Should you let, and they all came at the same time, should you let the guy who wants to use it for 1 minute go first, or should you let the guy who wants to use it for 1 hour go first? If you let the guy who goes for 1 hour go first, remember that the guy who wanted to go for 1 minute has to spend 1 hour 1 minute before he finishes, right? So compared to how much, so put it this way, the fraction of time he was actually working and the time he was waiting, having the shorter guy wait longer is actually a bit annoying. But if someone knows, I'm going to spend an hour here, but I'm only going to wait for 1 minute, it actually makes sense. And that's why sometimes we tend to pick shortest job first as a way to reduce response time, right? Now, priority schedule just means, and remember previously we were not looking at the priority value, and with priority schedule I'm doing a non-preemptive. Non-preemptive means that, for example, if someone is running, so P0 is running, and if it was preemptive, it means that if P1 showed up and P1 had higher priority, we would have to stop P0 and let P1 finish running. So that means whoever is having the higher priority to run, if we are doing preemptive, would always stop the other guys and run. But in this case, non-preemptive. So P0 is running for a bit, but when it finishes, it will ask itself so by the time it finished, there was P1, P2, P3, they can run, they are ready to go. They are all there. And who do we pick? And I would say, well, since 10, 2, 3, 10 is the highest priority, I pick that one to run. And when that one finishes, I ask myself, of 2, 3, 3, who has the higher priority? And there's P3 and P4, but since there are 2 of them came in at the same, one came before the, sorry, how do I put it? My words are not coming up. one came before the other. So I'll pick this one. So I just picked whoever showed up first. So I just picked this one to run. He has the same priority as P4. So it doesn't really matter about the time they spend on it. It's actually the priority. So we use the numbers to schedule them, right? And again, I do the computations. So for the priority schedules, usually the higher your priority, you'd expect that your response time would go down. But it doesn't guarantee that if you have low priority, you'd necessarily have low turnaround time. It also depends on when you showed up and if it's non-preemptive, right? So there's now round robin. Round robin, you remember, was when we give everyone a 10. So in this case, P1 shows up. When it finishes running, there's P0, there's P1. So it's, oh, then let him have a 10 because you just had a 10. At least that's how I coded this version of the scheduler. So whenever you finish running and someone else hasn't run before, I allow the person to go. So P0, P1, P2, P3, P4, and then I start again. But remember that some of them, so for example, P4 needed just one unit to finish. So when P4 finished, it didn't need to come back. That means that I now have only 4 people to deal with. So again, I go through P0, P1, P2, P3. But P1 needed just 2 units. So by the time this was done, I don't come back. When this one finishes, I don't go back to P0, P1. P1 is now out. So I go boom, boom, boom. And then, of course, this one runs and this finishes. And then I start alternating between those who are there. So the idea with round robin is for those people who are still not finished, we cycle. So we go one to the next, the next, the next, the next, and repeat. And when you finish, we take you out and we repeat. This is a very simple schedule. And again, I do the computations. Now, if you look at this round robin compared to the others, because we are giving everyone a short amount of time to run, round robin has the advantage that it would minimize response time. Response time here is 0. That's really impressive. So it means if you have interactive applications, so again, I would go to your current computer, which is an interactive computer. There's an interface. It would more likely be round robin than something that would say one person finishes running. Because imagine if it went round robin, that means Word will be running all the time, and then until you finish using Word, you can't use Excel. It's something crazy like that. But with round robin, it means everybody gets a slice of time, and you use it a bit. If you finish what you're doing, fine. If you don't finish, you have to give it up so another person uses it. That means that round robin is preemptive. Preemptive meaning I stop people. And this is an example of preemptive, meaning when I stop you, I go and pick someone. If it's round robin, I just pick someone who's the next person in the queue. If it were shortest job first with preemption, it means, that means that when someone with a shorter job shows up, I would stop everyone else who's running who has a longer job. If it's priority with preemption, it just means that anytime someone shows up, I would say, is he the highest priority? If he has the highest priority, you go straight into the running, and whoever is there who has low priority has to give up. Right. Now, I'm also going to do with 2 cycles. The previous round robin I was using 1 unit per cycle. But now I'm going to be using 2 cycles, so you can see how that goes. And it's the same thing. So when it was 1 cycle, he had to share. He went for 1, waited for everyone to run. P0 went for a second, waited for everyone to run, and then went for a third. But if I give you more time to run, that means you get to run twice, waited a bit, got to run again. Now, when we are doing the round robin, you'd see that the waiting time, so response time is very fast, but waiting time actually has increased a bit because for the first person, whilst for other schedules, when he runs, he finishes. For this one, as it's running, it's paused and it has to go and wait. Then it gets to run, it has to go and wait. So round robin may actually increase waiting time because you have to spend more time in the ready queue because you run a bit, you send back. And you can see for this one, if we increase the number of units you're allowed to wait, some people actually don't even get to wait anymore. So compare this where he had just, so P1, look here, he started to do 1, he was interrupted and got to run again. But when the units were increased, he runs and he finished, P1 finished, and then didn't have to come back. So you can play around. So some systems play around with how much time round robin gets to use when, or how much quanta is assigned. Of course, that's the computation. You can pause and see if you can get the same results. So if you want to test this out, of course, I said you can take the slides or pause the video and see if you can do it yourself. Now, there's a case sometimes when you have two or more processes arriving at the same time. So for example, if you look at this one, the arrival, and I mixed it up because I just want to create some excitement. So P1 actually came first, followed by P2, P3, P4, P5 showed up at the same time, P6 and 7 showed up at 9, P8 and 9 showed up at 11. Right. So this is a little bit longer. And so what we are doing is, and when someone says percentage of CPU used, you can tell that we are not actually using the entire CPU all the time. We wasted some time before we started using it. So you can look at the time from here to here and calculate how much or how often or what percentage of the time I'm on the CPU. Now, if you take a look at this, because P1 came first come first serve, they got to run. Now there are two people who showed up at the same time, first come first served. I'm just picking whoever in an array. It will usually be in some sort of array or data structure. I just pick the first thing at the top of the data structure if they are sorted. So picking this or picking that doesn't make any difference because they all came in at the same time. Some people ask me, they are very worried, oh, who should I pick first? Who should I pick first? You could just pick whoever showed up or whoever first, or if there's a tie, do a tiebreaker. Tiebreaker could be shortest job first, it could be whoever is at the top of the array, it could be on some other criteria. So you don't always have to just be pure first come first serve, but just be consistent. In this case, I'm just saying anytime someone shows up and there are two of them, if I look at the array, so this is my array of data, I'll just pick the person who is at the top of the array. And it would always be true, because if you have something like a queue, not a tree. For a tree, sometimes it's tricky. But if you have a queue, you can usually tell, or if you have an array, you usually have one person ahead of the other. So even though two people show up at the same time, I picked one of them to run, followed by the other. And when this one finished, I went through and said who came next. So you can see that whoever has a leading edge gets to run. And these guys, that means this would run before those. And when these finish running, then these would run. So this is with having multiple people showing up at the same time. That's the computation. You can try it and see if you got it right. Now, sorry, let me hold a bit. You can pause. Alright, so next is shortest job first. Very interesting, with no preemption. So P1 came in and was running. By the time P1 finished here, there was 1, 2, 3. So there was P0, P1, and P2 had come in. And the question was, who has the shortest job? And actually, it says P3, that just needed one, had the shortest job. So that went next. And after that one finished, we ask ourselves, who has the shortest job? And then the question is, P0 has the shortest job. So that gets to go. When P0 has finished, now there's the option of P2, this is P4, P5, P6, P7. Who has the shortest job? And it's now P4 has the shortest job. Of course, there are two people with the same jobs. But as I said, if it's in an array, you can just pick who is at the top of the array. It wouldn't have any difference I pick this or this, or depending on your criteria for picking. I just picked whoever is at the top of the array. So I run this one first. And then when this one finishes, I ask who has the shortest job. Right. And then I get to run it. And then again I ask, so you keep just asking who has the shortest job and pick one of them anytime you finish using the CPU. That's the computation showing the different jobs. I do this also with round robin. So round robin is very interesting because for this one, whoever came first gets to run. If someone came in, gets to run. But I'm giving priority to those who just showed up and have never got to run before. So I don't just alternate between P0, P1, P0, P1. I say, oh, P1 run, but P0 is running. While P0 finished, P2 had never run, so I let him run. And while that one was running, this one ran. And then I went through these two a bit. But by the time this one finished, someone had showed up. So I allow all the people who are new a chance to run. And then I start cycling again. And then I keep running. So anytime someone hasn't finished, you sort of give them, and you can see that I'm sort of going from top to bottom, and then I circle. So I'm going around in a loop from P0, 1, 2, 3, 4, 5, 7, 8, 9, and I go back to 0, 1, 2, 3. So that's how I'm sort of going through with the round robin, where multiple people arrive at the same time. So even if 2 people came in at the same time, like these 2, I pick one of them to run, and I pick the other to run because they came in at the same time. Right, so that's round robin. That's the computation. So you can check to see if you got it right. Right. Now, the other thing that's confusing or complex for some people is having multiple CPUs. When you have multiple CPUs, it means that you may have, or you can run 2 people who are running at the same time. Let's take a look. Right. So with this one, we have P0 came first, and I say I can run 2 people at the same time. So while P1 came first, P0 came first, it finished running, then P1 is running. P1 is running, but P2 showed up. Since I said I can run 2 people at the same time, you can see that for any time period, I'm running 2 at the same time. So when it finishes, I run 2 people who are also available. Then I run 2 people who are available. So this means I can actually run 2 people at the same time, and usually the more people you can run at the same time, the quicker you can finish your job. That's why computers now, we have this premium on having multiple cores. Same for your phones, same for so many other devices. They want to be able to run multiple devices at the same time. If we didn't have this, it would take much longer. If we couldn't run 2 at the same time, it would take much longer to run. And that's the computation now. Right. Let's look at shortest job first. Of course, one person is running. Since there's space, there wasn't even any contention, they were running. But when these 2 people finished, we had 3 choices to pick from. So when P1 and P2 finished, we had 2 to pick from. And since it's shortest job first, we picked the 2 shortest jobs we could find. Right? If it's just one CPU, we pick one. But we now can run 2 things, so we pick 2 things. And when that finishes, the 2 shortest jobs, one of them is of length 2, one is of length 3. But we can run them side by side. So we run them side by side. And when P4 is finishing, know that we can actually go and pick P7. So this is how you run 2 CPUs at the same time. Right? That's the computation. Right? This is round robin with 2 CPUs at the same time. So what I'm doing is I am always allowing people to run. So if you have a 10, so for example, P1 and P2, so P0 finished, I didn't get to use the second CPU. Then P1 came, but P2 wasn't there, so P1 is running. P1 gets to run again, because even though usually you would give up the CPU, there is nothing wrong because I can run 2 things at once. Right? But then, if there are 3 people to run, then the person who's been running on the CPU most recently gets to leave, right? And then someone else gets to have a chance. So I'm playing this game where I am doing round robin, but I'm also allowing 2 people to run. So it means every time I ask myself, who should I kick off the CPU? And I go and find somebody who's never run to come and run. And that's the computation. I think this is first come first serve with CPU. This is just a repetition, so you can ignore it. Now we also have multi-level scheduling. And sorry, this is a little bit longer than usual, but there is a lot in the scheduling class. Multi-level scheduling, so this is a step up, means we are combining multiple types of schedules. So we can say, oh, we can have a certain number of queues. For each queue, we can have a different algorithm. And we also have to decide some criteria to say, when do we allow people to enter specific queues? When do we allow processes to enter specific queues? And when do we move processes from one queue to the other? This is an example of different queues that I can have. So maybe I can say system processes are the highest priority. Interactive processes a little bit lower. I remember in class, I asked the question, if I have an interactive process and a batch process, which would you interrupt? And someone was saying, oh, I would interrupt the batch process. And I was saying, well, if something is interactive, it means the user is actually using it. So for those ones, usually we tend to move them up a bit in terms of allow the person to finish. So imagine you're playing a video game, or maybe you are clicking, but anytime you click the cell, it takes 10 seconds before it shows, or you're typing. And as you are typing on the keyboard, sometimes it takes some delay before it appears on the screen. It's very frustrating. So that's why we have system processes, interactive processes, the editing processes are next, followed by, so I just picked them from the text, but there could be different types of interactive processes, followed by batch, and then I said client processes. Maybe there's something you're running for somebody which is not high priority. So it means whenever you're running a program, you have to decide which of these does it get into. But the idea of multi-level scheduling is each of the different queues could, for example, system process could be using round robin. Interactive could be first, well, round robin, I think that would make sense. Round robin, batch could be first come, first serve. And client processes could be based on priority. So it means that the queues themselves have a priority, that is, we pick. So if you're a system process, we are more likely to come to you. So we are still picking. So we could say, oh, we pick one from here, one from here, one from here, one from here, one from here. Or we could say, oh, allow the system processes 5 units, allow these people 4 units, 3 units, 2 units. So we have multiple queues and we are picking from the queues based on some priority. And within the queues themselves, we are also having a specific scheduler running. So it's very interesting to have this one. Now, when it comes to scheduling, the first thing I'll point out is there's possibility for starvation. Now, if anytime there's a priority or shortest job or longest job, any type of scheduling where you allow someone to jump the queue, it means that somebody can be delayed indefinitely. Consider, for example, if I said I had a process that was supposed to run for 1 hour, and I'm doing shortest job first, and there are other jobs who have 1 minute, 2 minutes, 10 minutes, 6 minutes, 1 minute, 2 minutes. So that means everybody is less than an hour. It means that the person who wants to run an hour would forever starve. Now, the solution to starvation in this scheduling case is aging. Remember, starvation also happens for deadlocks and so on, but we're talking about scheduling here. So when someone says starvation, just ask, I know the concept, but where exactly are we applying starvation? So in terms of scheduling, we mean some process, because of priority or how the processes are getting picked, never gets to run. That means it would starve. It would not do anything, right? When that happens, as I said, the solution is to do some aging. That means that as the process stays on and on, its priority should be increasing so that eventually it will get to run. There's also the issue of processor affinity. Processor affinity means that some of the programs are running on specific processes. Let me pull out okay, so this is Process Explorer again. This is a real system, not like a fake system or anything. Let me sort these and pick one of these. Now when I say set affinity, so this program, Process Explorer, allows you to pick which of the CPUs to run on. And I know someone is asking, why would I want to know what CPU I want to run on? Now remember that anytime a program is running and it goes to a CPU, each CPU has cache. So cache is like local memory for just that CPU. So if somebody keeps getting sent to the same place, it would be easier because when it gets there again, maybe some of the information it was using is on the cache of the CPU. Right? So processor affinity is important. Now if a process keeps moving around from one CPU to the other every single time, it means that it's now more likely that it won't find things in cache. But of course, it also depends on the type of process. If it's a process where everything is reading is new and it's always getting a miss, then it won't make any difference. But for some things, processor affinity counts. There's also load balancing. Load balancing means, and again I bring this up and I'll go and bring the processes. It means that even though I have 4 processes, I would like, ideally, so let me pull the CPU graph. So it says I have 2 cores. Alright, so you can see that there are 2 CPUs. So one of them is running they're both running the same thing, and what it's saying is for the processes, we would like to keep them balanced. And you can see it's mostly, it looks sort of balanced in a way, right? So when the work is going up, so when this work goes up, it gives some work to this one, so it's running. So it means that the processor actually, it would like to balance it out, right? Now there are some reasons why you like to balance it out. Imagine, for example, you had 2 cars. Would you want one of your cars to be running at 500 kilometers per hour? Or would you like to say, oh, I have 2 cars, each one should take 250, 250. So if you don't push it too far, if you can even out the work, it would make it use less energy overall. So as much as possible, we try to spread out the work. When it comes to load balancing, there are two approaches. One of them is called push migration and pull migration. So it's all migration, but the question is who is initiating or how is the work being moved. If we say push migration, then it usually means that work is being pushed from the processor that is having a lot of load, pushed from the high load to the low load. Pull means that, so pull is the other way around, where we say the person who has less work can request for more work from other people. So the person who doesn't have any work, anytime he doesn't have any work, could say, oh please, can someone give me or share their work with me? And the push would mean whoever has the most work would say, hey, I have a lot of work, can someone else do some of the work? And try and shed some load, right? And you can combine these, right? So there's push and pull for load balancing. Now, when it comes to threads, there's this thing called process contention scope. That means that if I have a program that is running, so let me try and pick one of these processes, and I'll click properties. This is Microsoft Edge, and I click threads. Look at all these threads running in Microsoft Edge. Now, when Microsoft Edge has been given a CPU, it means that these threads will compete with each other, right? And that is usually what we call the process contention scope. That means there's a scope. So the scope would be within the process. Within the process, they are sort of fighting it out, trying to decide who gets to go next, right? But within the CPU itself, the kernel threads, so not in the user level, but lower. LWP means lightweight processes. If you don't know what it means you missed some lectures. Go read it up. We're spending so much time trying to just focus on scheduling. So look up LWP, lightweight processes. System contention scope means that when there are kernel threads that are running at the kernel side as well, they are competing, all the system threads are competing with each other. So there's a process contention scope, that means at the user level, and then the system contention scope, that's at the kernel level. The threads that, so a scope, so if we said, for example, what's the scope of contention? This is like, I think English would say, who else are you competing with? Maybe there's a job for head architect of a software company. What is the contention scope? That means who else are you competing with for that job, right? And if we said, oh, what is the contention scope for programmer? That means the programmer contention scope is different from the architect contention scope, is different from the engineer contention scope. So whoever is competing with the others, that forms a contention scope. And as I said, there are two, or at least two of them. Process contention scope, meaning for every process, the threads are fighting for that process, who should go next. And for the entire system, you can also have different system threads fighting for running time. Remember that we had this discussion earlier where we said we can have a mapping from user threads to kernel threads. We can do one to one, one to many, many to many. So that means there are two competitions going on, one at the user level, one at the kernel level, right? So that is with the thread scheduling. Now the other thing that we pointed out, and I said this before, is whenever you do I/O, you will have to let go of the CPU. It is not only I/O that will cause you to let go of the CPU. Sometimes you may ask for something from memory. And remember that there's cache between, so the CPU has a cache, and anytime it asks for information from memory, it places it in the cache so that the CPU can have it closer to it. So going all the way to memory takes much more time than going to the cache. And of course, going to hard disk is even much, much, much longer. So the idea is, if someone tries to access information in memory, it's sometimes possible that trying to access in memory will delay. And that would mean that the CPU is left idle. So what we call this, when there's a delay for accessing memory, is called a memory stall. Now there are some new processors where it can run two or more threads in the same core. I discussed this last time. Not every motherboard with CPU can do this, but some of the CPUs are capable of doing this. In Intel, it's called hyper-threading. So if you have hyper-threading, so for example, the machine I'm using now, it's a dual core, but I think it has, it claims it has 4 cores. It doesn't mean it actually has 4 physical cores. It just means that it can do 2 cores, and each core can do 2 threads. So it's like it can do 4 things at once. So depending, so when you are buying a PC or you're trying to analyze the system, keep this in mind. So if there's a memory store, It also helps you to schedule threads, so that anytime one thread is trying to access memory and it's delaying or may delay, you can schedule another thread to do the work. There's this other issue of instruction pipelines, but I'll not go too much into that. So let's just stop at that one. Now, sometimes when a program is running, it's difficult to know or to predict how long it will take. So what usually happens is, and there's this formula here. So there's tau, this is I think Greek, tau of n plus 1. So it means my prediction for your next value is equal to alpha. Alpha is a number between 0 and 1. So I'm going to look at what you currently did, and I'm going to scale that against my previous prediction. Right, so let's look at, so I did Excel, you can try this yourself as well. So the interesting thing is, anytime, so these are, I just did from 0 to 18, several values. So a computer is running, and anytime it comes in, it spends more and more time. So first time spends 1 unit, spend 1.5, 2, 2.5, right? And I start off by saying, okay, I'm going to guess how much time I think you will spend. So I said, okay, I'm going to guess that you spend 5 units of time. So first time you show up, I don't know anything. I said, well, let me guess you spend 5 units. Right. And when you spend 5 units, the other thing that I'll do is I'll also say, well, if you're going to spend 5 units, I'm going to try and do a prediction, try and scale to determine how do I determine your next time. And I would say I'm going to multiply your current time, the time you spent with me, by a fraction. And I'm going to multiply 1 minus that fraction by my prediction. And I'm going to add the two together to create a new prediction. So it's almost like saying you're going to visit my office, and I guessed maybe you spent 30 minutes with me, and when you came you spent only 20 minutes. So I would say, okay, I'm going to multiply half times the 20 minutes plus half times 30 minutes, and that will be my prediction for the next time. So it means that I have done a weighting. I've weighted how much time I think my prediction is worth and how much time I think the actual time is worth. Right. So with this approach, that means that I can use this. So every time I have a time that you come and spend with me, I will then take the tau from the previous version. So at time 0, I'll make a prediction and say tau 0, and I'm going to scale it and make a new prediction. And then the next time you show up, I'm going to say, well, okay, now you're going to show up at time 1. At time 1, I'll take my previous prediction and multiply it by a scale or a fraction and add your new fraction. So take a look at this. I will try to go through this again in class, but if you take your time and go through this, just do the calculation. You can see I'm trying to follow along. So this is my t, this is my a, my alpha times t of n. So I did half times, and then I of course did 1 minus alpha times tau. That's my prediction. So at every time you make a prediction, and then you do your scale up, right? And so it means even though you can't always tell, because for a lot of the computations I did, we knew how long things would take, but sometimes you don't know how long it will take because someone keeps coming and showing up. And this one is actually called an exponential average. So there are many ways to try and do prediction, and this is one of them. It's a little bit like machine learning in a way, because you're trying to do a prediction and you are weighting. So you're doing a weighting of what you currently see and what you've seen in the past, right? So that is this one. So for example, when alpha is 0, it means that I am ignoring you and I keep using my prediction. So if alpha is 0, it means whatever prediction I use at tau 0, 5, I'll be using that all the way through. What if alpha is 1? That means that at every time I'm going to be using your previous value to predict my new value. So think about that carefully. Right. The next, so this is the last topic for this, is real-time scheduling. So with real-time scheduling, we discussed 2 types of real-time systems: soft real-time and hard real-time. Soft real-time means the system will not be able to guarantee it will meet all the deadlines. right? And hard real time means it would have to try and meet all the deadlines. And for hard real time, usually there's this idea that if you don't meet the deadlines, there will be something catastrophic. So if you have a car and let's say you have your brake, you'd expect that if you hit the brake, it should treat as hard real time, because if you are hitting the brakes and it doesn't brake on time, you're going to hit a car. So it would say, well, anytime you hit the brakes, make sure that the car responds within milliseconds. But maybe you are just increasing the volume of your FM radio in your car. That is not a hard real time issue. That's a soft real time. You're increasing the volume, it took a few minutes to respond. Nobody cares. And that's why if you're buying a computer, some computers will tell you this computer is not for real time, or it's not for flying planes. I think that's the funny one that says don't fly planes with this computer. So now we know that the two types. It means you should be able to give me an example of some soft real time systems. So anytime you want something where you don't really, yes, you want a result, but it's not critical that it shows up at the exact time, it's soft real time. If the result doesn't come in and something catastrophic would happen, often would consider that to be hard real time. So you really need your results. Now for these, there are two types of schedules I'll be discussing: earliest deadline first and rate monotonic scheduling. I know the word sounds strange. Earliest deadline first sounds a lot like first come first served, and it's the same idea, except that now it's not about who came first. It's whoever has the highest priority. So for example, if there was a set of people maybe at the airport, right, and we are trying to get them to check in, to put their luggage, to weigh their bags and so on. Earliest deadline first would say who has a plane leaving soonest, who has the next plane leaving, who is on that one. Whoever is on that plane, please check in your bags, then you can go. And then when that plane leaves, then the next question will be, okay, now who next, or not when that plane leaves, like when those people have finished checking, we'll say, okay, who next has a plane coming up? And then that person also comes in, checks in their bags. And who next has a deadline? So it means that we would order the things by deadline. Right? So earliest deadline first is usually supposed to be able to handle dynamic priority. So things could be changing in priority, because the deadline, someone could come in with a different deadline, and that means that depending on what someone's earliest deadline is, your priority could be changing. Because if someone shows up with an earlier deadline, he will preempt you, so the priorities will be changing. Rate monotonic is a little bit more interesting, and I'll discuss that in detail a little bit. I'll follow on. But rate monotonic, just look at the word rate monotonic. It means that things are happening at a consistent rate. So maybe every 60 seconds, every 40 seconds. So processes are doing things. Monotonic means it's not changing. The rate of all the processes, the work they are doing, it doesn't change. So there are a lot of assumptions going in there. Now I'll be discussing the issue of latency, because when it comes to I think it was dispatch latency. Okay, I'll just go through. Event latency is, for when someone says real-time systems, the time between when an event happened and when the event is handled. So maybe I hit my brake, and the question is, when does the braking actually happen? Right? So there's this event latency. You do something or something happens, when you get response back. I also want to point out that if you have a computer, interrupts happen. So anytime maybe you hit the brake, an interrupt is sent to the CPU. So there's some time when the operating system has to look at it and say, what is the interrupt number, and what function should I call, what process or module should I load to handle the interrupt. That time when it's trying to determine what to do is called the interrupt latency. Right? So for real-time systems, interrupt latency is important, because when something happens, you want to make sure that the interrupt latency is small enough that you can run the internet interrupt service request, interrupt service routine, and then handle or run the process that's supposed to deal with whatever has happened. Right. Now, I expanded this from the diagram in Silverschartz's book. So what it's saying is, anytime events happen, so I think this is supposed to be an event happens, and then this is the event has been serviced. From the time an event happens to the time an event gets serviced, there are many things that occur. The first thing when an event happens is we need to do some interrupt processing. Interrupt processing means an event has triggered an interrupt, and that interrupt would involve a few steps. The interrupt occurred, we need to detect the type of interrupt, and we need to run the interrupt service routine. Right? So that means some little code has to run. So maybe if you hit the keyboard, there's a little piece of code that would run. When you unplug the power cable, something has to run. And some people have seen this. Maybe there are some laptops where when you unplug the power cable, the screen will dim. And when you close the lid, something happens. So for everything that happens, that it detects, it does something specifically. Right? So once the interrupt has been processed, remember that in the previous screen we said there's interrupt latency. The interrupt latency will be when the interrupt occurs and detecting the interrupt. Excluding, so interrupt occurring and detecting interrupt is the interrupt latency. The interrupt service routine itself is not part of interrupt latency. So there are 3 steps in here, and only 2 of them count for interrupt latency. Now, when we want to dispatch or send something to handle the interrupt, there's what we call dispatch latency, right? So the dispatch latency is actually the time between after the interrupt service routine has finished running. So we've seen the interrupt, we are handling it. But in order to switch from one program to another, usually there is this conflict resolution phase where we have to say, oh, who else is running? We need to stop them. So maybe you hit the keyboard. If you hit the keyboard, maybe you hit the power button. It means maybe we need to stop other programs from running, right? And we need to free up resources. That's called the conflict phase. So we need to figure out what the conflicts are, resolve them, usually by preempting, pausing, stopping people, switching where necessary. And then we have the dispatch phase. This is where we pick up the work that we need to do, set it up, and then we start executing the process that handles the real-time event, right? And we would hope that between when you ask for something, the event occurs, and when we respond to it, we are hoping that this is within some reasonable bounds so that the result is useful. Alright, so let's look. Earliest deadline first was easy. Let's look at rate monotonic. Rate monotonic is interesting, and I'm just going to use an example here. An example where I'd say one process happens every 4 seconds, another one happens every 10 seconds. Rate monotonic schedule. In that scheduling, what we'll do is, if your period is low, so if you happen frequently, the more frequently you happen, the higher your priority. There's a formula that we use to try and determine, is it possible to schedule you, right? Especially with rate monotonic. And it's just to say, it's similar to when we did Amdahl's law. We said, oh, we know that speed up is a certain value depending on the number of items. So for rate monotonic, we say that at CPU utilization, we are definitely sure we can schedule it if you fall below, and this is n, that's the number of processes, 2 to the 1 over n minus 1. Right. So let's do an example. So if we have a process, or 2 processes, one of them is running for 40 seconds, one of them running for 50 seconds. The first one always runs for 10 seconds, and the second one always runs for 20 seconds. The utilization would be 10 over 40, so 10 over 40, and 20 over 50. Right. So this is giving you a fraction. So that means process 1 would be spending a quarter of the time, and process 2 will be spending 2/5 of the time. And when we put the 2 together, we will get this utilization. So you can see that if someone gives me a schedule or a list of processes and execution times, if I add them up and I'm using up more than 100%, I know I can't schedule it. It's impossible. Right? But then, if I do an estimate, so if someone tells me, oh, there will be 3 people, there will be 4 processes, I do an estimate and I realize that I fall below using the formula. There's a tighter bound. I forgot the name of the person. I think there are at least 2 estimates. This is the slightly more open one. So this one would say, do the calculation, substitute 2. So if I have 2, substitute 2 into this formula. 2 to the 1 over 2. That's square root of 2 minus 1. And that's this. And that's 0.8284. Since 0.65, that's 2 processes, falls below this, I know, at least in this case, I'll know that, okay, it's possible that I should be able to schedule these. Now I increased, so I went from 1, 2, 3, 4, and I just keep calculating n 2 to the 1 minus 1 over n minus 1. And you can see that it's like a curve. It goes from 1 and quickly. So when there's 1, you can always schedule it. When there are 2, 3, then it means that for a real-time system, you can't use all the CPU all the time when you have rate monotonic scenario. And I even increased it. This is going from 1 and I'm doubling the time. This is at for 500,000. The value is 0.69. So it's almost like an asymptotic curve. So it's approaching a certain value. And this is giving me an estimate for how much I will have to keep the system free for. Now, it doesn't mean that just waste the CPU cycles. It just means that for a real-time system, I need to make sure that I keep, if I want to have rate monotonic scheduling, I need to make sure I keep some amount of the CPU free, right, so that I can do the real-time. So usually you do the real-time ones, and when you have extra time, you can do the non-real-time ones. Alright, so as I said, there's alias deadline first, and then also rate monotonic. So I think this has actually covered everything. So just scrolling all the way to the beginning. Sorry. CPU scheduling. So we've gone through different types of schedules, criteria for the scheduling algorithms. We were able to do some charts and graphs. We evaluated some of the schedules. So we did the chart. We looked at the different performances, calculated the average turnaround, and so on. We looked at special scenarios where we have single core, dual core, multiple things arriving. And we also looked at real-time scheduling, and in particular rate monotonic and earliest deadline first. I think it looks a little bit difficult. Don't just be reading this. I think it always helps. Just take out a pen, write, do a computation or two, just so it sticks. Because you can't just watch this like a video. Yes, you can, but when you see the numbers, try and sketch it out. So, for example, if I saw first come first served, I would sit down and try and explain it myself. If I saw round robin, I would sit down and try and explain it myself. If I saw this example, I would say, oh, okay, can I do the first come first serve by myself? And of course, if you go through, the answers are there, so you can check to see, do you have the right answer? So it's one of the chapters that can be long, but if you spend time working on it, you'd realize that it's actually not too bad. Right. So thank you for watching. I know this has been one of the longest videos. Feel free to pause, reverse. There may be 1 or 2 slides in there that will make sense because I didn't finish writing them. But I tried to cover everything in the CPU scheduling chapter. Thank you very much for watching.